So I will speak on behalf of myself, of course, but mostly on behalf of Fiona Tang, because she has contributed substantially to all the work that I will show here. And I was looking at the following presentations within these first sections of today that is related to the abatement, basically, and of the pesticide use, the inputs, and also the potential, reducing the potential contamination. So I think actually what I will present will be quite of interest also for the next two presentations by Nicholas and by Alain, I believe. So because we will show a little bit of the work in the past few years that is not just about actually the data sets that we have produced, but it's also about the use of this data and the implementation into assessment tools for overall environmental contaminations. So the outline is relatively simple. I'll just give the context and the fundamental questions to our work. And then I will detail a little bit, but not too much, the approach and the way we develop the data sets that we're using and the models that we use. But in particular, I will show three examples of modeling that make use of those data. And in particular, two examples would be the process-based, fully mechanistic and full-size models. The other one will be more empirical based, but it's still a global scale assessment of contaminant pollution. Then I will just very quickly summarize and open the floor for the questions. So we use about 4 million tons of active ingredients every year globally. That nominally is about equivalent to 0.5 kilogram per person per year, and it's about 1 to 2 kilograms per hectare per year, right? So these pesticides move through the environments. They are very ubiquitous and they can be found in the soil, surface water, groundwater, atmosphere. But most importantly, they have been found also in remote areas in the Antarctic or in glaciers, in high elevation in the mountains, and so on. That really makes or gives the idea that in reality is not just contamination by pesticide is not just a local problem, but this problem is open to the entire environment. So the negative effects on non-target organisms have been quite already investigated and highlighted, in particular to insects, amphibians, and other type of invertebrates in soil and also aquatic ecosystems. But there is also the aspects of exposure to human subjects, and it's quite well known that some pesticides have an endocrine disruptive effect, or they can be carcinogenic, and they may also induce some neurobehavioral disorders. But the important thing is that the pre-birth exposure to some pesticides can decrease the IQ. And the last point that you see here is that a decrease of 1 point in IQ can cause a 2% reduction in the lifetime economic productivity of that subject. So the repercussions of pesticide pollution is just the environment or the residues that we can find in the environment, but it's really the exposure and the consequences that the exposure may have on the human subject or also other non-target organisms. Now, the questions, probably the most important questions are these, right? How many active ingredients there are on the market and how many are approved? But I have to say that in general, this type of questions have an answer because many countries have registries. Some countries, those registries are public, so we can access actually that information on how many are approved, how many are around and how many are approved. The most difficult questions to answer are rather these ones, which are what are the application rates, where and when they are applied, on which crops, the frequency, the methods of applications, because that these questions are related to the way in which actually these pesticides diffuse through the environment. But most importantly is that we know that we use pesticides, but where do they go at the end after they have been introduced in the environment? This is, in my point of view, as an environmental engineer, probably is the most important questions, and I will show you later on slides in which we report on work we have done about these aspects. And the other questions is a little bit wider, and I think actually Alain may be later on in the third presentation may actually say something about these aspects, but is to what extent are pesticides part of economies and global economies. Now, the reason why I ask this question is that we do have an understanding about pesticides. We know that we use them, we know that they move through the environment, but we still have a big missing link on the food production systems, I would say. And I think actually everyone will agree on what I show here. So you take, for example, the typical primary food productions, and we all know that they have an equivalent in terms of greenhouse gas emissions, land use, contaminants or nutrients like fertilizers and water. But the key point is that there is no equivalent yet agreed or tabulated about the pesticides used to produce 100 grams of beef or 100 grams of lamb and so on. So now the major limitation for which there is this big gap is that there is no quantification, shared quantification of the active ingredient used that is geographically distributed. And I may let it for the conversation later that country level data, like the one, for example, provided by the FAO, they are not enough to understand the environmental processes that lead to the dispersion of pesticides and the consequent exposure of non-targeted organisms. So that's the reason why we started to fill in this gap first with this data set, which is called PestChemGrade, and is actually a collection of data that reports the high and low estimates in application rate, at least as of 2015, even if we produce some projections to 2020 and 2025, but the one of 2015 are tested and quite validated. This dataset uses or reports the 20 most used active ingredients in 10 cropping systems, and that means 95 collectively active ingredients. The 10 cropping systems include more than 100, nearly 200 crops. It's a georeference dataset with a resolution of 10 kilometers by 10 kilometers, and the total mass that we release in this data represents about 85% of the global total pesticide use in the US, but by inference, we can say also globally. And we can say it's global because actually it covers about 200 countries and territories. So now to produce this data set, we mostly use the first data set that you see here is the USGS PNSP project that provide the basic information for this type of geostatistical inference at global scales, but we coupled it with so many other data of environmental, socioeconomic, and hydroclimatic features. And also we used this data to produce this data. We also conditioned this to the governance, like for example, bans in particular country of particular active ingredients, and also biotechnologies, such as, for example, the use of particular pesticides on GMO or pesticide-resistant crops. Then we also tested, we validated at least in part the data that we released with some publicly available datasets. The workflow that we use to generate these datasets is very complicated. It is represented here on the right, but I'm not going to go too much into the details for limited amount of time. This is an example of the data that we distribute. Is the application rate of glyphosate on corn, and this is the high application estimate. And you can see right away that it's not country-based, it's georeferenced, so only involves the surface area that actually has agriculture, and that agricultural land is treated with that particular active ingredients. But overall, the data set is nothing but a collection, let's say a matrix of maps in the 2 dimension, which is active ingredients and cropping systems that can be used for many, in my point of view, for very multiple purposes, whether these be data analysis or modeling, assessment or policy making. You may think about as many as you think actually of this. But in particular, I'm quite interested in the second and the third one. That means modeling, diagnostic, in particular modeling, and assessment, environmental risk analysis assessment. And these are the two uses that I will show you in the next few slides. One case is about the glyphosate and AMPA contamination at global scale, and the other one is the global pesticide budget that is still preliminary, but we are working on that, and I have some preliminary figures to show you. The second one is the work mostly by Fiona, really directly, is the environmental risk analysis that was mentioned before by the chair. So for the mechanistic modeling of pesticide contamination, we use a computational environment which is called BARTSIM, and it's something that we have developed here in Sydney. It's a full-scale mechanistic model that basically uses or solves for the mass and energy conservation laws and continuity laws, and is applied to all the phases in the soil in the environment, which is solid, liquid, gases, and also biological. And it can describe any arbitrary chemical or biological species, and has multiple other features, which I will not be able to introduce in the details now, but you may refer actually to the user manual and technical guide. It's quite versatile and powerful in my point of view, because as long as you are able to design a reaction network of a particular substance, in this case, pesticides, then this reaction network can be deployed over geographic scales, and I will show you very, very few details. So these are two reaction networks that we have developed in the past, mostly by Daniele La Cecilia, who is actually attending the workshop because I saw him before. And so basically this reaction network describe all the cascade of mass flow, starting from the parent compound down to the building blocks of those molecules. And you have to imagine that each one of these black arrow is a biochemical or chemical kinetic reactions that we calibrated with experiments and we integrated afterwards. So in this case, we have developed quite sophisticated reaction network just for glyphosate and atrazine, but for the other pesticides, we haven't yet because it's very complicated, and development of this requires quite a lot of work. But once you have this reaction network, the solver actually accounts for basically a vertical soil profile, including atmosphere, topsoil, root zone, and downwards down to the aquifer or bedrock. It's up to you in designing the geometry of the problem. And in this computational domain, a number of processes are accounted for, including advection diffusion, of course, but also all the other equilibrium reactions, such as the one listed down here. When we do our assessment at the global scale, this is not enough. We deploy at a global scale. So basically, we take this prototype or archetype vertical column, and we duplicate it, we clone it over a georeference grid, three-dimensional at global scales, and we feed this grid with all the possible boundary conditions that are needed, like solar radiation, for example, rainfall, evapotranspiration, in this case, also the pesticide application rate that we have developed with the PESCAP grids, right? Once we have duplicated this on a three-dimensional global scale grid, we run it on a supercomputer, and we are able to either focus on a local scale, like a field, or plot, even plot scale, like a square meter if we want to, but most likely we use this approach to look at regional, continental, and even more likely global scales. Now, the next slide, I will show you an animation that is actually the one that we produced for the glyphosate contamination. The molecule of interest here are two. The one on the left that you see here is glyphosate. The one on the right is AMPA, which is the byproduct of glyphosate. You know that better than me. Now, the first three rows are three different depths in the soil, in the root zone. And the last row is the leaching rate of those pesticides and residues below the root zone. This is a simulation of 50 years at a relatively high resolution geographically that we conducted to understand what is the residue of the parent compound glyphosate and what the residue is of the byproduct. And you may know that AMPA is much more recalcitrant than glyphosate. So the real issue we found in this work was that the problem in itself was not really the glyphosate, but actually was the accumulation in the soil of this byproduct. And you can actually see from the animation, from the animation here, that, oops, I don't know how to get back to this animation. Okay, that only the topsoil is interested, and only partly the mid soil is interested to the residues of glyphosate. But when it concerns to AMPA, all the soil column gets affected because it's not biodegradable, basically. So we ended up with 4 variables of interest. One is the biodegradation efficiency of glyphosate. The other one is the leaching rate, the residue in the soil, and the persistence. And this is just the long-term average of all the variables that we retrieve from the simulations, where we can highlight the hotspots geographically for these 4 variables. But our interest here was to end up with a criterion that could collect these 4 variables as indicators for the hazard overall, hazard in the contamination by these 2 molecules. What we found is that about 40% of agricultural land is actually affected by a mid-risk, which is quite wide in my point of view, but mid-risk, it means that only 2 of these 4 variables reach a threshold of concern, while there is only 1% of the cropland that is at high risk, which is actually all the 4 variables have produce a concern. So that was a first application of the mechanistic models that we deploy for pesticide contaminations. The second, like I mentioned before, is only preliminary, but is really a global pesticide budget that we designed to be similar to what actually other scientists in other fields do, which is the global carbon budget, for example, or the global nitrogen budget. There is no such thing like a global pesticide budget yet. So the objective was to determine the dynamics of not just one pesticide, but all of them at global scale, using a mechanistic model like the one I introduced before. We wanted to complete a budget, meaning that knowing the inputs, we want to know where the losses are, what is the accumulation, and where the outputs are. And we wanted to determine also what are the endpoint environmental compartments that receive the residues that is not degraded in the environment, right? So in this case, again, we use a global grid at very high resolution, but the key numbers that I want to put here is that we accounted for about 200 big catchments globally. We neglected the small catchments with the small river, and we accounted for about 200,000 kilometers of rivers that receive by runoff the pesticide residue that is not degraded or does not go below the root zone into the aquifer. In this case, however, we model the full depth down to 55 meters. So the input variables, again, is Pescam grids, and of course, all the soil properties, hydroclimate, boundary conditions, the river geometry, and again, flow rate from either shed, and so many other variables. We are talking about terabytes of data. And the main outputs that we wanted to address was actually the mass of active ingredient in soil, either absorbed aqueous or gaseous, the mass that is biodegraded, what leaches below the root zone, the yield into rivers, and the discharge to oceans. Really, to just go back to determine the endpoints that receive pesticide moving through the environment. And also in this case, I think I have these animations is very preliminary, but it shows the geometry of rivers that we have accounted for, including all the basin for the catchment for those rivers. And what you see here is the runoff of undegraded pesticides that is present in the aqueous phase in soil, expressed in terms of milligram of pesticide moving from one grid cell to another per every square meter of grid cells, averaged over 5 days of simulations. In this case, we did, I think, 30 years of simulations. Is an enormous simulations. But this is just one of the possible animations that I can produce. And this is just the surface movement, is not the application rate when you see this reddish blobs coming up is actually the movement of pesticides. Now, we did the first land budget in the root zone, and of about the 1 teragram of pesticide applied globally, we found that about 90% is lost and 10% stays in the land as residue globally. Now, the losses here include about 82% of biodegradation, so pesticides that are consumed by soil bacteria and they say they disappear more or less. But there is a 10% of leaching below the root zone that we assume that is not biodegraded anymore because the biological activity at 2 or 10 meters depth is basically null. And there is about less than 0.1% of yield into rivers. The residue in the soil is mostly in the adsorbed phase to soil organic matter, and there is a little bit in the aqueous phase, very little bit in the gaseous phase, and nothing, practically nothing in as a precipitate salt. Now we are interested in the endpoints, right? So we focus on the yield, on the yield into rivers, because the yield to rivers is the input in the rivers, and we wanted to track what happens in the rivers after that. So there is about 800 tons entering the rivers every year. Of this, we have about 97% of losses, and a little bit of residue is about 2.5% residue. It means in aqueous solutions in the river, in average annually. Now, the losses are that only 1% is biodegraded, according to our first estimate, and the rest is substantially discharged into oceans. So we wanted to visualize a little bit better this. So this figure here shows the number of kilometers, so the kilometers, the length in kilometers of rivers that receive a particular input of pesticides at a given rate. And there is about 6,000 kilometers that receives more than 1 ton per year. We are talking about river reaches, not the entire river. So these are 5,700 kilometers of river reaches that receive these inputs of pesticides. And this is an average, however. It goes seasonally because it depends on the rainfall, on the slope, on the elevation, and on many variables that we explicitly included in this model. But the important figures in my point of view is where those pesticides go at the endpoints of the river, and how much of this mass, what is the distribution of the, let's say, of the mass discharged into oceans. What we see here is just to give you an idea of the amount of mass that goes. And what we see, in my point of view, is quite interesting because Europe has generally a low discharge into ocean, and it's very likely related or correlated to the policy for pesticide use and persistence in European countries. What we see something slightly different, let's say in South America, where the policies are a little bit loose, and maybe also in Southeast Asia, South Asia, and very East Asia, like China, which is probably related to the amount of pesticide used to satisfy the food demand. Of course, Oceania and Africa have much less because probably the environmental conditions lead to less discharge rate into oceans. So I just want to go quickly because the time is passing by very fast. So we conducted another type of assessment, which is the one that was mentioned before. So we calculated the predicted environmental concentration in 4 compartments, again, groundwater, surface water, atmosphere, and the soil. But this time we use a semi-empirical model, which is called EPRIP. And we also coupled this with the no effect concentration that are calculated based on the liter concentration, the median liter concentration. Then we calculated the risk point as the log transform of the ratio of the PEC and PNEC, right, in the 4 compartments of the environment, which is identified by the K. And then we calculated the risk score as the maximum of the risk point throughout all the 4 compartments of the environments. Of course, these analyses were replicated throughout all the grid cells globally, and we ended up with the risk class for the based on the risk score. Now, of course, because it's logarithmic, then it can be smaller than 0. So everything that is smaller than or equal to 0 was a negligible risk, up to the scale that is high risk when the risk score was greater than 3. And we found a geographic distribution again of the risk of environmental contamination that may affect actually non-target organisms and the environment. So the overall result was that about 31% of the global land is at high risk. That means a risk score greater than 3. It can be also greater than 4, as you see from the map. And about 74% are at some risk, which is something smaller than 3. It, on the scale goes from medium to low or negligible. And interestingly, Europe has the largest land fraction at high risk, which is 62% of the land. And Asia has the largest land area, like absolute value, at high risk because, of course, of the extension. In particular, China is a big country and with a big cropland area. Very quickly, we also tracked the number of active ingredients that may pose a concern. And we found that 60% of the land has a risk of contamination by more than one active ingredients, and about 20% by more than 10 active ingredients. The geographic distribution by continent is also represented here, but I'm not going to go into the details now. So I just quickly summarize. I think I'm about on time. So there is no standard yet for countries to report as an inventory or as a registry the mass of individual active ingredients used within that country, even though some countries release public databases, but these are still limited by the sampling frequency, the time window available for the active ingredients. And we know that in Europe and maybe in other countries, there is also the privacy issue for which those data cannot be released if they are georeferenced, basically located. So what we have is that reconstruction and data reconstruction, like I state here, so far is probably the only way we have to just have an idea, may not be precise, but at least we are able to have an idea of the pesticide use. This data allow for a number of investigations, and in particular the use of process-based models like the one we showed you, allow for both diagnostic or prognostic analysis of pesticide contaminations. But other environmental risk analyses are possible, such as the one we showed just a couple of slides before. And they are also very powerful when it comes to public health exposure and potential adverse effect on public health. There are a number of things I would like to say, but probably there is no time. So I have to close it here and I have to open maybe time for discussion or questions. Raja, I don't remember, but I let it to you. Yes. And I thank you very much for the attention.
Thank you so much, Federico, for this nice presentation and the impressive work. It was really nice to see these maps all around the world. So David Makowski kindly accepted to discuss your work. So David,
yes,
you have the floor for 5 minutes, please.
5 minutes, okay. So indeed, the presentation was very exciting. Thank you for this. I have several questions. So maybe the first one is it possible to use your modeling framework to evaluate the impact of different types of farming practices? Because of course, pesticide use depends on the crop species, but it depends as well on different type of management practices. For example, if you grow maize using a no-tillage system with GMO, you don't use the same type of pesticides compared to a system where you use tillage without GMO. So yes, is it possible to do that with your modeling framework?
Thanks, David, for the question. Is a good one. Now let me explain a little bit more. Now the model that we use is very highly mechanistic. I didn't mention that we consider as input knowledge also the land use, the land cover, the type of crops, the root density profile for the individual crops, the seasonality in the irrigation, for example. We use the solar radiation to model the heat flow and therefore the temperature of the soil throughout the entire profile. So let's say the response of the biological reactions that lead to the degradation of pesticide is fully and explicitly accounted for. So to say, the bacteria sense the temperature, sense the pH, sense the water content in the soil when it's too dry. In an arid region, for example, the biodegradation will be lower. This said, we did not investigate a scenario, for example, for changes in the agronomic practices in this work before, but absolutely, yes, this is one of the potential scenarios that can be analyzed with this model. I want to add that one of the things that we were working on initially, then we abandoned it, was to investigate the climate change effect on the contaminations, because we know that there will be some regions they are going to experience more precipitations, so the mobility of these pesticides will increase, and some other will become arid, hotter, so maybe the biodegradation rate will be lower. So in the same way, or in a similar way, different agricultural practices can be included. And I add one more thing: in no-tilling or tilling practices, the soil carbon may change over a reasonable time scale.
Yes.
In this model, we account also for the soil organic carbon as a co-metabolite for the biodegradation. So if there is no carbon in the soil, there won't be, or there will be very minimal biodegradation of these pesticides. Meaning that if we imagine a scenario of tilling or not tilling, the outcome of the diagnosis, let's say, of the thanks to the model, will show whether the pesticide contamination will increase or will decrease. But I can anticipate to you that if you have a practice that conserves the carbon in the soil, that conserves the water in the soil, very likely the contamination level may decrease. So the residue level may decrease.
Okay, thank you. So I have another question concerning the data set itself. So of course you did not have time to explain all the details concerning the development of your global data set, but in Europe and in France, of course, pesticide use is a very hot topic, and a lot of people are striving to develop a reliable data set concerning pesticide use. And one issue we have is the difference between the locations of the places where pesticides are sold and the places where pesticides are actually applied by the farmers. There are differences both in space and in time. How were you able to deal with this issue?
Oh, okay. Again, this is an enormous question, because Fiona, I know that Fiona is working really on these aspects of the trading of the pesticides, but not at, I mean, at local scale, no, mostly at global scale. So if David are considering the let's say France, for example, then very likely is not easy to reconstruct the path for these pesticides to move, so where they are produced and where they are sold. But across stations, across nations, this is possible.
Okay.
Now, the localization of the application rate in pest chem greens was based on the actual location of the crops. And it was estimated by accounting all 20 or more environmental variables.
Yes,
There's a covariate for the geo inference.
Okay. And so we don't have a lot of data on actual pesticide use, but we have some, because there are some surveys conducted, I think, every 4 years in France, for example, but also in other countries, concerning the actual pesticide use of farmers. So we have a few local data concerning actual pesticide use, with the pesticide use rates as well. Do you think it could be a good idea to use this kind of survey data to evaluate, in fact, the quality of your data set?
Absolutely, David, absolutely, yes. There is one of the difficulty we have had, and is the validation of our estimate. We only found a few national data sets, in particular the UK data set, the Australian one, and another one from South Korea or South Africa, I don't remember, that is actually reported in these publications. But the amount of active ingredients in those data sets was very minimal. And the time window for which those data released was also very minimal. So there are plenty of gaps. My message, maybe at the end of my presentation, would be also that the more real data there are, the better it is.
Yes.
Not just for to validate pest chem grids, but to even produce a much better one, a much shared one that involves many more communities, not just our initiatives, but the ideal case would be as many data as possible, the better it is.
Okay. So thank you for your inclusive message. I think my time is off, so I give the floor to the other people. Thank you.
Thank you, David, for the questions, and thank you, Federico, for the answers. I had almost the same question as David in terms of validation, because I'm also working on. We have a national project in France on pesticide reduction, which is coordinated by Julie Supervi. She will discuss the presentation later, and Alain Carpentier also could say more words on this project. And I was impressed by your work, because we are working on the national scale, at the French scale, and I see how difficult it is to manage the data, because the term pesticide is a heterogeneous word which includes a lot of things. Herbicide, fungicide, and herbicide, also insecticide, and also it's the toxicity is different from one product to the other. So we are working on how to manage this thing, and we are working on the idea you mentioned. We are trying to see what are the impacts of climate change on pesticide use in France. So we have started with the postdoc right now, and I hope we could discuss on this later. And I keep in mind the idea of David of validating your work at the French scale. The French data is not perfect, but at least it's local, and it could be a good way to collaborate maybe later. We have a lot of questions. We have Nicolas, Julien, Lois, and Nicolas in this order, please. So Nicolas, if you would like to ask a short question, and Federico to have a short answer, please.
Okay, thank you. Can you hear me?
Yeah.
Yes. Thank you for the great presentation, and it's really impressive. And I have two short questions. Would it be possible to extend the pest chem grids dataset back in the past, and for example, back in the 60s? And the second question is, do you think it would be possible to combine this data with biodiversity data to study the effect of pesticide use on biodiversity at a global scale?
Yeah, thanks, Nicolas. The answer is yes, it's possible to reconstruct the past. We actually did it down to 1985, if I remember well, but we have not released the data. So it is still possible to do it. And I mean, we just were not so sure of what we were producing back in the past. So we decided not to release them.
Okay.
But I can tell you that we are working on maybe an update to pest chem grids where we want to reconstruct the past. The answer to the second question is whether this data can be intersected with the biodiversity data. And the answer is yes, actually, it's one of the potential use that I was referring to initially. So for example, intersection with other data sets. And I don't remember, maybe Fiona can say very quickly, but I don't remember whether for the risk analysis, we actually already accounted for the biodiversity of some particular species like amphibians, earthworms, and birds and other organisms. But I may actually have a conversation with you later. Yeah, however, the answer is yes, and it would be super valuable if something like that would be done very explicitly and very, very specifically, but still at global scale.
Okay, thank you.
Thank you.
Julien, you would like to ask your question directly?
Yeah, thank you. Thank you for your talk. About biodiversity, interaction between biodiversity and pesticide, just for your information, a national expertise will be delivered in May, next May. So we are in the process of reviewing all the parts. So you can have some answer about the interaction on non-target biodiversity.
The French scale?
It's yes, no, this is the expertise. So
okay.
This is a review of publication.
Okay.
My question is about the hydrological pathway. So in your mechanistic approach, do you consider only leaching, deep infiltration, or you consider also runoff and tile drainage? Because when we saw the Corn Belt in US, this is mostly influenced by tile drainage, and it shortcut the water flow and transfer directly the pesticide to the river.
Yes, we do consider leaching, the movement throughout the vertical column and the horizontal flow. We use the curve number method from the USGS to calculate the runoff of water. And from the runoff of water, we consider what is in solution for the pesticides. Then it will be carried through the land actually as runoff. The other question was, you were referring to the freezing towing, right? Or am I right? Or
excuse me?
The second part of the question you were referring.
This is about tile drainage.
Drainage.
Yes.
Well, no, probably no. We did not consider. I mean, the drainage below, drainage like leaching below root zone is accounted for. Other type of draining or drainage in agricultural soil, no, we did not explicitly accounted for. But I'm not sure I completely understood actually.
Yeah, because in the US, this is in Mississippi and Missouri. This is mainly drain, artificially drain, and it shortcut the water pathway directly to the river. So it influences a lot.
No, we did not account for that explicitly. So we did not.
Okay.
Thank you, Julien and Federico. Lewis, please. Short question and short answer.
Thank you very much, Federico and Fiona. A very impressive work. I wonder if you have an idea, only an idea, about the share of pesticides consumption, at least at the country scale, of that are not included in the inventories that are banned pesticides. This is very high, or now it's much lower?
I think actually we attempted to do that type of estimate because the FAO, for example, does not report all the countries. It only reports like 100 countries, if I remember well. Even if they are the biggest country, there is a number of countries that do not report. So the 4 million tons estimated on the base of the FAO data, it may be an underestimation. And if you look into the paper, the PestChem Grid paper, I think there is a section in which actually we produce the total global estimate. I don't remember, I have to be honest, I don't remember specifically whether it is 10 or 5% above what is reported in the official documents.
Okay, thank you. Thank you.
Yeah.
Last question, Nicolas, please. Short one, very short answer.
Thanks for your presentation, very interesting. So my question is, pesticide risks are very heterogeneous, land use is very heterogeneous, and probably the risk profile of certain regions is very heterogeneous, so that you have more leaching and so on. In your analysis, did you identify some kind of potentials to relocate, for example, certain kind of agriculture practices, or that you could give to policymakers to say basically it's very risky to grow this kind of crops in these regions. It would be wiser to grow this somewhere else, for example.
It's a good question, and it probably can be taught as one of the outcomes, such as the one in this figure that highlights the hotspots where the highest risk occurs is really geographically located. So this already may be used as an indication to the policymaker, saying that, well, guys, be careful there because the expected risk, if we do that, is likely high. But we did not investigate whether that risk, if those practices can be relocated somewhere else where the risk is going to be lower because of environmental conditions. So your question is very interesting. It could become actually a paper by itself, a very important paper, where it is an example of policy, the effect of policy or good policy making.